Hello and welcome to the second section of this course regarding numerical methods. Here we'll be discussing iterative methods to finding solutions to problems. Now here on top of the page we'll see four diagrams here. The first two diagrams on the top have a convergent solution, and the two diagrams below in the bottom half of the page don't have a convergent solution. Why? Well, the function itself here, its first derivative is between 0 to 1 in the top left corner. In the top right corner, the derivative is between -1 and 0, not including -1 itself and not including 1 itself on the left. So, that's the first derivative evaluated in that interval that we are working with. Is as long as its absolute value is less than 1, then we may have a convergent solution. Now, what are we talking about exactly? Is certain functions that we take the output and we feed it back to itself as the input. So, for example, here, we took x1 here and we evaluated it. It hit the curve here at this point. And this red line, this line is where y is equals to x. That's the line where the output would become the input. So this value of y would be evaluated. That means that it would be reflected in this line here and will be x here. If we evaluate the function again here, then we take the output and feed it back. We come here. And this loop tends to converge somewhere here where we find our solution. Okay, so this was a rather abstract example. Let's get to a numerical example where we'll see how it works. In general, in A-level maths, you don't have to consider any of these values because the function will be given to you where either it will converge, and if it doesn't converge, then the question wouldn't be asking you to prove anything. So it's rather more simple than you think. Okay, as I said, these first two on the top are convergent, these next two are divergent. Right. Alright. I've created another example here where you may not be familiar with this equation, but that's one way of figuring out the square root of any number you've been told. Let's say we want to find the square root of a. Constant a doesn't change in this equation, but we take some value that is roughly near to the answer that we are looking for. This index of n plus 1, the subscript, means that the next value what comes out of the right hand side equation will be our input in the next iteration. Okay, as we said, we are going to feed back the output back into the function itself. So you're not required to memorize the details that are coming up on the page, but the square root of a can be rearranged like so. We could write x squared as 2x minus x squared, and we could divide by x, and we could subtract x from add x to both sides. So, and we divide by x. So that's where that formula comes from. Now, how do you use this in your calculator? How can you use the output rather than slowly going through and feeding back step by step? I'll show you a quick way. So let's look at that in this example. Let's say we want to evaluate this function near 0.5. You type 0.5 on your calculator and you press equal sign. Now 0.5 is stored as the answer on your calculator. Then you start typing the function as so on your calculator. 2 as half. You're going to type this in your calculator. Half, open a bracket, type the answer, find the button that shows the answer. Make sure you don't evaluate it. You only press it once, and you press plus 3 over the answer, and now you press execute and execute again. What you notice that you should get these values that are coming up. After a few iterations, what you notice is that the value on the calculator no longer changes. It converges towards the answer, which is roughly 1.732. What happened behind the scenes was that your calculator took the input of the first iteration and took it as an answer and put it back into the same equation again. So we bounced around the curve and we got back and we got further and closer to x5, which is 1.732. You don't have to consider the diagram, but you know that what happened in the calculator was that we were looking for the square root of a number. If you look back, that number that we found the square root to was number 3, because that's the number that was we substituted for the value of a. Now, you can find the square root of any other number as long as you start evaluating at a, at a number that is roughly within the range or close to the actual answer. Now, if it's far, far from the answer, of course, this formula wouldn't work and your answer will diverge. You can try this for yourself again with some other number instead of 3 and test whether the answer comes out to be right or wrong. Alright, so I'll see you in the next example. In this example, we've been given that f of x is a quadratic. We've been asked to show that the equation or the function has a root, and it actually, before we show that it has a root, we can show that it can be written as x equals to 4 take away 1 over x. This looks nothing like the original function itself, but we can go ahead and start looking at the function and we can try to rearrange it. How do we do that? Well, if we take x squared to one side of the equation, when f of x is equal to 0, then we will have x squared equal to positive 4x minus 4. This is allowed operation to do, dividing by x, because we were told that here x is not 0. So knowing this assumption that we are not dividing by 0, we are allowed to do this. And once you divide by x, you see what happened is that now we can use this sort of a recursive formula to find roots of the equation, where f of x would have been equal to 0. Let's see how it works. The example tells us to use a value between 3 and 4. So what we do, we can take x naught to be 3. As I said, you can store 3 and press equal sign on your calculator, and it will store it as the answer for you. Then you're going to type the right side of this equation. You're going to write 4 minus 1 divided by answer. Then that will help you to put the first value of 3 as the input into the equation, evaluate it, and you get 3.66. If you press equal sign again, your calculator automatically feeds it back into the same function, which was 4 take away 1 over x, and then you get the next answer. And what you notice is that if you repeat this process enough times, you may get a convergent answer. The convergent answer here was 3.731, which turns out to be only one of the roots of this equation. If you want to figure out the other root, you have to choose a number that is close to the root itself. Let's look at the next example. In this cubic polynomial, we are to show that one of the roots lies between 3 to 4, in the interval of 3 and 4. So, to show that the root lies within this interval, all you have to do is show a change of function, change of sign in the function itself. We have two alternating signs, so that is enough to prove that the equation has a root. Now, in part B of the question, we are asked to use this iterative formula to calculate the value of x1, x2, and 3, and so on. Once we start with x0 to be 1.5. So, in this case, we are not too sure how this function came about, but it's easy to see that if you set this function equal to 0 and take negative 3x squared to the side, then you divide by 3 and you take the square root, then you would have come up with this formula. Some questions ask you to prove this iterative formula. Some questions just simply want you to use it. So let's look at the example. Once again, you store the value of 1.5 as the answer, and you start substituting those values into your function. You type in answer rather than 1.5 because you want to use the quicker method of evaluating the next iteration and the next iteration. And what you end up with is 1.33, 1.25, and 1.2. Okay, this is slowly converging towards one of the roots of the equation, or rather the polynomial. Then you can use number 4 as your answer. You clear everything in your calculator, you type 4 and you press equal answer. Then the number 4 is stored as one of the in your calculator's memory as the output and an input that can be used in the function. So you type in your calculator square root, and you are going to rather use answer cube minus 2 times answer plus 5, and you put a bracket around this expression because you're going to type in divide by 3. Then you should be able to work rather quickly for the next iteration and the iteration after that. What you end up with is 5.4.5, 5.4, 7.12, and sadly this other part does not converge. So what you learn from this method is that one of the roots is close to 1.201, and unfortunately you've been told to use an answer that doesn't give you a convergent result. So I hope that was helpful. I'll see you in the next video.